Hello, everyone. This is Dr. Lennon, and we will be looking at 6.6 probability this week. So these are some specific applications to probability distributions. So first, we'll be looking at what makes something a probability distribution, and then also what are the measures of center. On the PowerPoint, there's also some stuff on the normal distribution, which we'll talk about, but typically, so the normal distribution is another continuous curve where you can use integrals and improper integrals to find the probabilities of certain events. But there's a lot of tables and technological resources, so no one really kind of integrates these by hand. And there's a lot of parameters involved, so the integrals can just be a little bit messy. But anyway, we might talk a little bit about that next time, but we won't go through that part of the PowerPoint today. Okay, so 6.6 probability. So again, rather than typical variables, we have something known as a continuous random variable. You can also have things like discrete random variables. So discrete random variables means it only takes on a finite number of possible choices. Like if you roll a die, there's only 6 possible outcomes. You could roll a 1, 2, 3, 4, 5, or 6. So that would be a discrete random variable. Whereas a continuous random variable, there's a whole interval of values that are at your disposal. So let's say you were waiting at a drive-through. You could say the continuous random variable would be how long it takes you to receive your order. And you could calculate the probability that it's anywhere between, say, 2.5 minutes to 7 3/4 minutes, something like that. So you have a whole interval of values. And because we have that interval, we call it continuous. And that's when the integral and the techniques of integration come in handy that we've learned about this semester. Okay, so there's an example again. On this one, we're looking at the lifetime of a battery at the bottom, and the way that we write the language is we have the probability, and then inside the parentheses we list the interval. And what those things are going to be is they're going to turn into your limits of integration. So basically, we need a function that's going to model our distribution, and then we compute the probability by doing an integral with those limits as our limits of integration. Okay. So because we're talking about probabilities, there's a couple of rules of probabilities that are going to be important. The first is that all of our values, if you integrate over any specific integral, you have to get something non-negative. It only makes sense to get probabilities that are either 0 or positive in value. And then the second thing is if you integrate the entire space, you should get 1, because the probability of all the simple events happening is 100%. So if we want to consider the probability of some smaller interval, that should be some value between 0 and 100%. So that's what it talks about on the slide when it says, since we have something representing a proportion, the probability has to be between 0 and 1. So probabilities as a decimal, again, can be converted to percentages. So probability of, say, 0.45 would be 45%. Okay, so the probability density function, the density function definition is exactly what we talked about, but instead it's going to use the language of mathematics and the integral. So suppose something, we have a discrete continuous random, sorry, not discrete, I don't know why I was saying discrete. So every continuous random variable x has a associated probability density function. So again, that's just going to satisfy our 2 rules. So the first is that if you so it's defined, so the way that you define that probability is just integrating from a to b, as we talked about. And we can see, so below is an example of a normal distribution where you're talking about the area it's saying is the probability that the height of the woman is between 60 and 70 inches. So basically you can integrate f of x from 60 to 70 and figure out the probability associated to that event. Okay, so the only thing that we need to do to check really, in general, it says a probability density function of a random variable satisfies the condition that the function is greater than or equal to 0 for all x. And since the probabilities all have to be between 0 and 1, if you integrate the entire space, so here it says negative infinity to infinity, it doesn't necessarily have to be negative infinity to infinity. You might have a function that's domain is smaller. In that case, you just integrate the entire domain. If you integrate the function over its entire domain, it has to come out to 1. So if those things are satisfied, then you have what is known as a probability density function. And some of the homework questions that you have just ask you to verify that very fact. Is it a probability density function? So that's probably what we'll see coming next. Okay, so that's what we have here. So we have this function f of x equals 0.006x times the quantity 10 minus x. And so here, again, as I said, we wouldn't have to go from negative infinity to infinity because the domain it's telling us right there is from 0 to 10, and it's 0 everywhere else. So if we want to verify that this is a probability density function, what we have to do is we just have to integrate that function from 0 to 10. And then part B is asking you to find a specific probability. So the probability that your continuous random variable is between 4 and 8. So in that case, you're going to perform the same integral, but you're just going to integrate from 4 to 8 rather than from 0 to 10. So let's look at A. So for A, we're integrating this function from 0 to 10. Again, notice it says negative infinity to infinity, but really that just means all the domain. Since it's 0 everywhere outside of 0 to 10, then that's what the limits become. And our function 0.006x times the quantity 10 minus x, we just want to expand that. So basically distribute your 0.006x, and once we've distributed, then we're just applying the power rule where we add 1 to the exponent of x and then divide by that value. So we get 0.006 integral from 0 to 10 of 10x minus x squared. They pull the constant out rather than distribute it. It'll come out the same. So when we integrate 10x, that'll end up being 10x squared over 2, which is 5x squared. And then the antiderivative of x squared will be x cubed over 3. So we get exactly that antiderivative. And then again, since this is a polynomial, the second limit, when you plug that in 0, everything vanishes. So we just plug in 10. So 5x squared becomes 5 times 10 squared, and then x cubed becomes 1,000. And we get our value. So it comes out to 1, so that means indeed that the thing we're looking at is a probability density function. So the second part, we have we're doing the probability that it lies between 4 and 8. Now, there's no need to reinvent the wheel here because we've already found the antiderivative. So if you look at the very top line of the slide, 0.006 times the antiderivative there, 5x squared minus 1/3 x cubed, that's all you have to do is change those limits. Rather than 0 to 10, we're going to change 0 to 4 and 10 to 8, and we can go ahead and evaluate without having to go through the whole process again. So they write down the integral, but we again already know what the antiderivative is. We're just switching the limits, and here we'll get 0.544. So that means the probability that your continuous random variable is between 4 and 8 in this example is 54.4%. Okay, so average values. If we want to talk about an average value, so let me walk you through an example with a discrete case. Just basically average values if we talk about. So what does an average value look like? For a discrete probability distribution. Basically, it's just a weighted mean. So let's think about, I don't know, maybe you have something with 3 possible outcomes and you weight them. So your discrete random variable here is x. Let's say it has possible outcomes of 1, 2, and 3. And then we have probabilities associated to each of those outcomes. Maybe we have 1 happens 0.25 25% of the time, 2 happens also 25% of the time, but maybe the third outcome is more likely, and that happens 50% of the time. I don't know why I wrote a 3, because I was looking at the associated value. So your idea for your mean, which here would typically be using the notation x bar, what you do is you just take your probability weight, multiply it by the value, and then add. So you would have 0.25 times 1 plus 0.25 times 2 plus 0.5 times 3. So this comes out to 0.25 plus 0.5 plus 1.5. So that gives us a mean, in this case, of 2.25. Now, notice that's a little bit different because we have these associated weights. That changes the value of the mean from what you would expect if you just did a traditional average. Meaning, if you added all the x values together and divided by the number of them, so if you added 1, 2, and 3, that would be 6, and if you divided by 3, you would get a mean of 2. But that is under the presumption that they all are equally likely to occur. If you have a case where they're not equally likely to occur, you run into having to use a weighted mean, which is what we do here. So what are we really doing when we're trying to find this weighted mean? We're basically adding together, so this sum just means add all these things up, x times p of x. Okay, so this is the discrete case, kind of like when we're using Riemann sums. So if you imagine having some continuous probability, so some probability graph, and you wanted to figure out what its mean was, you might call its probability density function p of x. What we do then is we just integrate from, again, over whatever the domain is, negative infinity to infinity of x times p of x dx. So this is the idea for finding the mean of a continuous distribution. So what we do is we just look at the discrete case and kind of mirror it with the typical continuous objects. So let's go back to the PowerPoint and look at average values. So again, this is just kind of a so we have a phone call, a corresponding density function, which they're calling f of t, and then a sample of n people. So none of them had to wait more than an hour. So in this case, the domain is 0 to 60. So again, they're subdividing with Riemann sums. So they're adding a lot of machinery that we don't really care about because we're not going to use it. So when they talk about multiplying all these things together, essentially what's happening is we're getting our x times our p of x that we looked at. So, and then they're adding them all together. That's great. But so they show it a little bit differently, but basically they integrate from 0 to 60 of t times f of t, and they call this the mean. So this is what we talked about that I just wrote down. So I did x times p of x, they're doing x times f of x, but we're going from negative infinity to infinity. And this lowercase Greek letter mu, this is the very common letter that is used for population means and probability and statistics. You will see lowercase mu as the letter representing mean, and you'll see lowercase sigma representing standard deviation. So if we want to integrate, if we want to find means of continuous random variables, we need to use this formula. So a lot of times you might see substitution popping up here because, again, now we're multiplying by x. May not. I mean, if you had two polynomial function, you could just distribute the x, and then you would have just the power rule being applied. But yeah, again, we'll see. Okay. So the mean, again, long range average value. One of the measures of centers we see. So here we go. Find the mean of the exponential density function. So they're using c as a constant here, but it would work fine if you just replaced it with a letter. So maybe we should go ahead and do that. Let's look at. Let's go ahead and see how that would work if we replace it with a letter. So let's look at this example. Let's say example let's say find the mean associated with the probability density function, PDF, and we'll say f of x. Oh, they're using t in that problem, aren't they? So let me just use t since they're using t. F of t is equal to, okay, so part of it is just 0 if t is less than or equal to 0. And what did we say? Let's pick some other letter. Instead of using c, let's use the number 5. Let's say 5e to the minus 5t if t is greater than or equal to 0. So let me see. Let me make sure I copied that down correctly. So greater than or equal to here. Yeah, but negative. Negative. I forgot the negative. One note. Here we go. Okay, no, I didn't forget the negative. I got it right. So actually, we should. This one does not need to be underlined. All right. That was the only issue. Okay, so basically, to find the mean, we just need to integrate. So our domain here is given by this t greater than or equal to 0. So my mean mu is going to be the integral from 0 to infinity. So we do have an improper integral here. And I need to multiply this 5e to the minus 5t by t in front. So I get 5t e to the minus 5t dt. So I'm using that from the definition up here. Weighted mean is x times p of x. So I have to include a t there. So again, this is just an improper integral. So we want to replace that infinity by a limit as t goes to infinity. So this is the integral from 0 to t of 5t e to the minus 5t dt. And then if you remember, we have a product of two different kinds of functions, 5t and e to the negative 5t. So this is going to be an integration by parts. So we want to let u equal 5t and dv equal e to the minus 5t. So du is 5 dt, and v is minus 1/5 e to the minus 5t. So then our integral becomes, we still have that limit as t goes to infinity of, so we do uv minus the integral of v du. So we have negative e to the negative 5t. So the 5 from u, oh, I forgot the t in front, minus t. But the 5 will cancel with the minus 1/5 and just leave a negative in front. So we have minus t e to the minus 5t minus the integral of v times du. Now we'll have two negatives, so this will turn into a plus, and the 5 will cancel with the 1/5, and we just have the integral of e to the minus 5t dt. And again, this is all from 0 to t. So then we end up with the limit as t goes to infinity, and this is minus t e to the minus 5t minus 1/5 e to the minus 5t from 0 to t. So this ends up being the limit as t goes to infinity of minus t. So instead of e to the negative 5t, let's write that as over e to the 5t, and then minus 1 over 5e to the 5t. And then we want to subtract. If we plug in 0 for t, the first term is 0, and then we get minus 1/5. So what's going on? Well, it turns out, so exponentials, as we know, go to infinity really fast. So which means the denominator of each of the expressions in the first pair is getting very large. So this term goes to 0 and this term goes to 0. So that's all we're left with is the negative 1/5, which comes out to 1/5. And I think somewhere I must have forgot a 5 because this should be coming out to 1. So let's see, where did I forget a 5 at? The integral of v du. So did I forget my initial 5? Let's see. uv, so I have uv minus the integral of v du. Sorry, we're not proving it's a probability distribution function. We're just proving we're finding what the mean is. So we didn't do anything wrong. So therefore, the mean of f of x is 1/5. So i.e. mu equals 1/5. And that's our answer. So let's go back to the slideshow and make sure that they got the same thing. So, okay, back to the old presentation mode. So, okay, so rather than, in our example, we used 5 just so things would be a little bit more clear. They're using C here. Again, they're applying the definition, and then they integrate by parts. So, again, they have that constant of integration, but we're doing a definite integral, so we don't have to worry about the constant, the plus capital C. So they do their limit, and they if what we got matches what they get, since instead of having a 5, they have a C, their mean should be 1/C. So they do the integral. Again, they say x over e to the cx goes to 0 because essentially the exponential quantity in the denominator of the fraction is going to infinity much faster than the numerator. So there you see the 1/C appearing, everything else goes to 0, and they get a mean of 1/C, which is exactly what we got, except for using some actual integral values. So there we go. Let's go ahead and look at one last example. So this is an application. So that's what's known as the exponential probability distribution. And so now if you know the mean of the exponential probability distribution, you are able to write down exactly what the distribution is. So they say, suppose the average waiting time for a customer's call is 5 minutes. Find the probability that call is answered during the first minute, and find the probability the customer waits more than 5 minutes. So we're using the distribution. Since 5 is the mean, now 1/5 will be the value of the constant, right? So basically, if you know the mean is 1/C, if you go back to the distribution f of t here, in our example, we know the mean 5 is 1/C. So if 1/C is 5, that means C is 1/5. So we can replace this f of t with 1/5 e to the negative 1/5 t. So we have our probability density function here, and we just need to integrate for each of the two examples. So the first one they asked, what's the probability of calls answered in the first minute? We would just integrate from 0 to 1. And for the second one, the fact that they wait no more than 5 minutes or more than 5 minutes, I can't forget which, we need to integrate from 5 to infinity or 0 to 5, whichever one they said. So the first minute, as mentioned, we're integrating from 0 to 1. This is one of those things, again, where we already know what the antiderivative looks like, so we can just go ahead and plug in the values. But yeah, so that's what's going on there. So the antiderivative, we just need to be replacing it and then dividing by negative 1/5. So maybe I'll demonstrate that as well. So let's look at this example. So let's just look at computing that integral. So let's say compute. What were we doing in this example? They didn't really show the steps. So they had the integral from 0 to 1 of 1/5 e to the negative t over 5 dt. Well, you can just pull the 1/5 to the outside, and then we're just applying the exponential rule. So this is the same as negative 1/5 t in the exponent. So remember the rule, the integral of e to the kx dx is just e to the kx over k. When we're computing a definite integral, we don't need to worry about the constant of integration. So this will just be 1/5 times negative 5, because you have to divide by negative 1/5, which is negative 5. Remember, dividing by a fraction just means take the reciprocal, and then we have e to the negative 1/5 t, and we're integrating from 0 to 1. So this is going to come out to negative e to the negative 1/5 plus 1. So that's what you put in your calculator, and that is what's giving you your associated probability. So let me just grab my calculator and see what that comes out to. We'll see if we're getting the same thing they do. So 1 minus e to the negative 0.2 comes out to 0.1813 about. So 0.1813. So that's the same thing as 18.13%. So that's the probability that we would have a call received in the first minute. So yeah, so we get exactly the same thing there. So when they integrate, they get all the same steps, 1 minus e to the negative 1/5, 0.1813. And then again, for the next question, finding whatever the case is, we can use the same antiderivative we had in the second line of this slide. So it says find they wait more than 5 minutes. So we're going from 5 to infinity, which just makes this an improper integral. But the antiderivative will come out the same. Usually what's going to happen is one of those terms is just going to vanish. So we're looking at the limit as x goes to infinity of minus e to the minus x over 5 plus e to the negative 1. So the limit of the first term there is going to go to 0. So essentially our probability is just going to be whatever the value of 1 over e is. So it comes out to 0.368. So about 37% of the customers wait more than 5 minutes before their calls are answered. You might have expected that number to be 50% because 5 minutes was the average value, but it turns out that that is a different notion. If you're integrating and getting exactly half the probability, that is the analogous notion of the median, not the mean. So the mean is just the weighted idea where you're looking at the integral of over the domain of x times p of x, whereas if you're looking for the integral to equal half the probability, that's what's known as the median. So why don't we stop here today, and next time we'll go through some more examples where we verify that things are probability density functions and also compute some probabilities. So if you have any questions on any of the homework problems, let me know, and I will go ahead and include those in the video next week. Otherwise, we will do some more of those examples and maybe talk a little bit about an example with a median, which I don't know if there are any in the homework, but we just talked about the notion right now, so we might as well include it, and also maybe look at some normal distribution examples. So this is Dr. Lennon signing off. Have a great week.